Welcome to the Quantum GotSec screencast. Today we are learning to secure messages using laws of nature TM. So if you're interested, open up your IDE, stay here, and let's code together, and let's move from small brain to big brain in a world of quantum computing. Okay, so as you might recall, last time we built a quantum random number generator. We will leverage it today. The code for everything we did in a form of a convenient Jupyter notebook will be shared in the description. So yeah, all the power to you, taking all excuses from the smart kids. So remember, do not be lazy. If you are not smart, we can work on it, but if you are lazy, then stop being lazy. Okay, so back to the topic. Today we are doing the first part in implementing one of the protocols in quantum key distribution. The protocol itself is called BB84 from the year it was described and the first letter of last name of folks who actually created it. And before we even talk about the protocol, let's first lay the ground or lay the foundation to understand what actually we are trying to solve. So first, private key cryptography. So imagine that you've written a secret message that you would like to only share with your friend, maybe sister. I don't know what your situation looks like, maybe even a wife or a husband or whoever. But either way, you want this message to be very secret. Maybe you're bad mouthing somebody else and you don't want that somebody else to know about it. Either way, to keep it secret, you decided to somehow scramble it and pass the message in a scrambled form to the counterparty, and the another person knows exactly how to unscramble it, and then they can read it. Of course, the whole process of scrambling slash unscrambling is very not trivial because you need to agree on a way that only you two will know and nobody else. And in a world of interwebs where there is a lot of eavesdropping and adversary actors, this is not guaranteed. But the method itself uh, might be thought about as a key, meaning that you lock the message with a key and then you unlock the message with the key. The problem remains how to share the key. You can share the scrambled message, maybe nobody can read it, but if your counterparty cannot read it, then yeah, you send him or her basically a set of random bits. Okay, so the that's the idea behind the private key cryptography. You have a message that is encoded, and you have a key that needs to remain private, meaning that only you and the receiver is allowed to know the key. So we, of course, now solved one problem and created another one, and that's how to distribute the key. And that's exactly whether quantum key or Q key QKD comes into play, and that's exactly what the protocol of BB84 is here to help us. Uh, as I maybe said, the whole implementation will be split in few screencasts, uh, but this is only to help everyone to stay focused. I know that people rarely can focus over 15 seconds, and this will probably again be quite long. So I am here to help you, as I said. So in here, we will implement the noise-free version of BB84, which is idealized because in the real world there is noise, as you probably even hear right now in the background. But the noise there refers to a noise within a channel, and channel is basically how you communicate from person A, which we will call Alice, to person B, which we will call Bob, as it is standard in cryptography scenario. So we will today implement following steps. The first one is Alice generating two random binary strings. Then Alice will use those strings to create a quantum state that she will send to Bob. Bob then will try to decode the message, basically using very fancy guess decoding technique. Then they will exchange special strings that it will allow them to basically decode the message. And in the next episode of Quantum Gotek Screencast, we will add eavesdropping Eve that will try to eavesdrop and basically interfere with our communication. So let's get to it. So, as I said, the first step is to create two random binary strings for Alice. Of course, we need our quantum random number generator. And we can already declare simulator from Cirq. Great. So the PRNG generate binary array. That's now we need to select a length, and it turns out that even this number is not, well, it can be selected quite arbitrarily, but in order for stuff to be easier to present and actually even to prove, we will select a number that is a multiplicity of 4, and that's because while testing the string in next steps, we will need to drop some of the bits. And then we will need to do it again. This is exactly because we drop half on average and then half on average. This is why we have the multiplicity of 4. So we will select n for starters of 4, and the string length will be 4 times our selected number. Great. And Alice B. Yeah, so we using the power of quantum randomness that we harnessed in last screencast, we generated two strings, Alice A and B, and now we will encode, prepare our quantum state in such a way that will allow us to then, yeah, leverage the BB84 protocol, or rather, we will prepare the state according to the BB84 protocol. So, okay, we of course need to prepare some qubits. The same number as the string length, and we will give it prefix of q underscore. And as we will be operating on the qubits, then for that we need to prepare a circuit. We'll call it a quantum channel. Recall that channel is basically a means of communicating from person A to B. Okay, so we've got our qubits, we've got our channel, and what we can do now is to prepare the state accordingly. So the idea is quite simple here. If, as you might recall, all the qubits are in ket0 or simply 0 state, and if we want to turn them at 0 to 1, so we need to use the X quantum gate, which is basically, or simplifying a little, a quantum analog of NOT gate. So it turns 0 to 1 and 1 to 0, among other things. So if Alice A, that's the A string that we actually want to encode, is 1, we will append to a quantum channel gate X, the quantum analog of classical NOT gate, and we will reverse the qubit with at this particular index. Okay, and if Alice B is 1, then what we will do? So the idea behind the BB84 protocol is that if the string B is 1, then we will change the so-called computational basis of the qubit, but that is very important, but it is more grounded in science, and I don't want to dive deep into science right now. So basically what H-gate does, as you might recall, it turns the 0 qubit into this state where it will return 50% 0 and 50% ones when we will measure it multiple times. Or rather, we will measure multiple qubits in that particular state. So we will simply apply H-gate. And this is because in the next step, when Bob will be decoding it, if you apply H-gate twice, you get to where you begin. And this allows you to encode and then decode message accordingly. Okay, we are golden here. What we can do right now is to print the quantum channel and see if we are on the right track. It seems so. Okay, as you might see, we are missing, for example, the Q1. And why is that? This is because the Alice A string and Alice B string were probably 0, and they are simply not yet the part of the circuit. And it takes quite long time to execute because importing Cirq takes a little bit of time. When you will be working with the workbook I've prepared, then it will be very well quick. So do not worry and be patient. Okay, so the next step 3, if I recall correctly. Yeah, this was step 1. Preparing the state was step 2. Now we've got ourselves into step 3. So what happens here is Bob will use the mighty technique of guest decoding. So he will randomly generate a string uh, Bob B that he will treat analogous to the Alice B string. And what he will do in range, if Bob B index is equal to 1, then he will assume that Alice also used H gate on that particular qubit and apply its second one to effectively decode the message, removing the randomness from the measurement. Of course, if he is wrong, then he will get a non-reliable message, but he more or less has 50-50% of having a good shot. Okay. Great. And at the end, we add the measurement that Bob's perform, and we can see the our quantum channel. Please note that everything will be random from the beginning. We need to import Cirq once again. Give it a moment. Meantime, okay, there's no need for our meantime. So as you can see, we have the HH gates. So here Bob guessed correctly, and Kyoto we can obviously check, but right now I want to build the intuition that the H gate was applied once, and that means that Bob will not measure it correctly. Well, he will not be certain about, he cannot be certain about the measurement he takes. And at the end, we have the measurement, the lines connecting the M measurement gates basically tell us that we will get a singular result from the simulation. Instead of having each qubit sent one by one. And as a important side note, it can be actually, Alice can prepare a qubit, single qubit one by one and send them one by one to Bob. This make like physical implementation in a dirty real world more feasible, because you need actually less qubits and less complicated quantum processing machines. That's a side note. We are more interested right now in being fluent and building intuition, like with software development on a higher level of abstraction. Okay, so our simulation result. Simulate the quantum channel. Fun. And that's Bob guess decode. Measurements, and it will be Bob measurement. Yeah, let's copy and paste it. Cool. So we have our step 3. The last thing that will be even more important is that Bob will take Alice over a classical authenticated channel that he received and measured the state. And this can be done over classical, meaning non-quantum authenticated channel. It's a channel where you are not. It is basically public, meaning you do not have privacy guarantee, but you can be sure that the person that is sending the message is actually who is sending the message. So the adversary cannot act or impersonate either Alice or Bob. This will be more important when we will be introducing Eve. Okay. So now what will happen is that they will only they will exchange the B strings with each other, Alice and Bob, and they will only keep the indices of Alice A and Bob guess the code when the B strings are matching. This is because if the B strings are matching, then they did perform the very same operation. And if that is the case and there was no noise involved, then it means we are golden and the messages should be the same. And every bit is has every pair of bits have, if I recall correctly, around 50% of being the same. So it's actually quite good. So on average, they will end up with a string of length 2n. Alice B is equal to Bob B. Alice kept A. This is basically a subset of Alice A that has matching indices. And Bob gets decode with the same indices. And those strings should be the same. I will now copy from the notebook small piece of code that simply prints the B string of Alice and Bob, the A string that gets the codes, and the one that they kept. Okay. We've got ourselves an error, probably a typo. It's, I think, measurement, not measurements. Or yeah, it was a typo. Sorry. Okay. A good thing is we can see that the resulting strings are the same. I will move myself up. Okay. So as you can see, the B strings are different. That means that, for example, on the 0th index, Alice did not apply H-gate but Bob did. So the Bob cannot be sure about the measurement, and indeed he measured the wrong bit. But if the same information, if the same basis as in the B string was used, then they end up with the same result. So this is simplified and idealized part of the BB84 protocol. In the next screencast, we will introduce noise, we will introduce Eve, we will be talking about no cloning theorem, and we will basically start where we left. And yeah, that will be really fun. In the meantime, in the description, you will get link to the notebook. You can fork it, you can work it on your own, play with it, have fun. Yeah, and as always, remember it's a beautiful day to code and do not be lazy. Hope that uh, you moved from small brain to big brain today a little bit. Uh, yeah, subscribe, share with your friend, share with your mother, whoever. Thank you.